we now have to solve this equation. You see, this was the equation that we obtained in the last lecture, and we will try to solve this equation. And once we solve that equation, we can get a solution of this equation, because I will take that solution and calculate psi of x multiplied by e to the power of minus I e t by h cross, which is guaranteed to obey that equation, and therefore, I would have a solution of this equation. So, how do I solve this equation is the next question. For that, I am going to divide my space into 3 regions. When I say space, you see, it means all values of x running from minus infinity to plus infinity. So, this region which is to the left of the box is referred to as region 1. Maybe to make it clearer, I should remove this. This is region 1. What is region 1? It is the region where x is less than 0. The particle, if it exists there, it is outside the box. And further, this region which is to the right side of the box, I shall refer to as region 3, while the region within the box itself I shall refer to as region 2, and we are going to solve this equation. But then, of course, you see, outside the box there is no probability of finding the particle. Why? Because the potential energy is very large, and we are saying that the particle has some amount of finite amount of energy, not an infinite amount of energy. So, there is no way in which the particle is going to go into that region. So, that itself tells me what the solution should be in this region, because if I am going to say that the probability of finding the particle outside the box is 0, that definitely should mean that the wave function for the particle in the region 1 as well as in region 3 must be 0, because only if the wave function is 0 would the probability, which is I star psi, will be equal to 0. So, I have immediately solved the Schrodinger equation. I mean, if you want, you can kind of verify it by substituting the solution in here to just to make sure that everything is fine. See, suppose you are in region 1, then what will happen is that the potential energy is very, very large in region 1, right. I said it is infinity, but of course, I mean, it is very, that means it is a very huge quantity, a very large quantity. So, here you have a very large quantity, and then what this says is that multiplied by psi must be equal to E. E is not a very large quantity, it is some finite number, finite value, multiplied by psi u. So, a very large quantity into psi must be equal to, this equation has the appearance, a very large quantity into psi must be equal to a very small quantity into psi, and the only possibility is that psi must be 0. So, therefore, the equation is automatically satisfied if I say that psi is equal to 0. So, after having solved it in this region as well as in the region 3, what is it the solution? I say that psi of x is equal to 0 here in this region, as well as in this region psi of x is actually equal to 0. So, therefore, what is left is to solve it in region 2, and in region 2 what happens to this equation? Well, I will have to remove this also. Well, in that region I know that this is the equation, but I know that in that region V of x is 0. So, therefore, what will happen? I will have minus h cross square upon 2 m dou square upon dou x square operating upon psi of x is equal to E psi of x. This is the equation. Now, here again, if you look at this partial derivative notation that I am using, strictly speaking, this is not necessary, because this partial derivative is going to operate upon psi, which is a function of x alone. There is no other variable on which psi depends, and therefore, there is no reason for me to use the partial derivative notation. So, I could have as well written d square upon dx square without making any error, so to say. So, let me rearrange this equation slightly. Well, all that I am doing is I am multiplying throughout by the inverse of this. So, I take 2m h cross square to the other side effectively. That is the equation. Okay. Right. You rearrange this. This is the equation, and we would like to save the trouble of writing this again and again and again. So, therefore, we are going to say, okay, I am going to call this k square. This 2m e by h cross square, I will refer to it as k, I will write it as k square, and therefore, this is the nature of the equation. So, I have defined k square and it is now very straightforward. You see, this is just an ordinary differential equation which can be easily solved. You can actually verify that a function of the form a constant, which I will denote as a sin kx, satisfies this differential equation. It is only a question of just differentiating this function 2 times. You will see that this equation is automatically satisfied by that function. So, a sin kx is a solution, but that is not the only solution. You can have another solution which is of the form b cos kx. This is another possible solution. This is not surprising, because if you have a second order ordinary differential equation, there are 2 independent solutions, and the most general solution would be a linear combination of these 2, in which you add the first solution with the second, and therefore, we will take the most general solution and say that that is my psi of x. Okay. But then suppose I have found the solution, I mean I have the solution and the values of a and b at the moment, they seem to be arbitrary. But suppose I find the solution and make a plot of the solution, all the things that I have obtained. What I mean is I am going to make a plot of psi of x against x. See, this is a plot of v of x against x, right, and now I want to make a plot of psi of x against x. And the box is of length L. So, therefore, the box extends from x is equal to 0 to x is equal to L. So, if you think of plotting psi of x, what is the result that you would obtain? Well, in this region which is outside the box, I know psi of x has to be equal to 0. So, therefore, the plot is just the horizontal axis itself. So, that is the plot, and in the region where x is greater than 0, again the result is the same. So, this will be the plot, but in this inside the box, so the solution is of the form a sin kx and b cos kx, that is how it is. So, if I want, I can easily make a plot of this function, because sine function and cosine functions, they have oscillatory, I know that. So, maybe what is going to happen is that I will have some such appearance, because they are oscillatory, maybe they will do that, correct. This is the kind of behavior that you will expect. But then when you look at this, you would feel a little bit unhappy. Why? Because you see, if you look at this function, you look at the point x is equal to 0. At this point, if you are approaching from the left hand side, what will happen? The wave function is always 0, and even close to very close to this point, the wave function is actually equal to 0. While on the other side, suppose you are approaching x is equal to 0 from the right hand side, from this side, what happens? The value of the function actually approaches that value in the way I have made this plot, and therefore, what happens? The wave function actually changes in a discontinuous fashion at x is equal to 0, and that is something that we do not want, right. This is something that I have described earlier. Okay. So, this is something that we want to avoid, and in fact, we will consider this in more detail when we think of particle confined to a box of finite depth, right. If outside the box, I will assume that the potential is not infinity, but finite. So, there it will be much more clearer, but at this point what I want to say is that you see here there is a discontinuity in the wave function. As you cross the point x is equal to 0, the wave function suddenly jumps from the value 0 to a finite value, and we do not want that. So, in order that the wave function should be continuous, which means that there should not be any sudden jump in the wave function when you cross the point x is equal to 0, what should happen? The wave function's plot will have to look like this, correct. This will be the correct wave function's plot. Right, the one that is shown with the yellow curve should be the correct plot. Why? Because that satisfies the condition that the wave function is continuous everywhere along the horizontal axis. And if that is the way it is, what is the condition that my wave function within this region should satisfy? At x is equal to 0, its value must be equal to how much? In order that the function is continuous, see from the left hand side the wave function is 0 everywhere, and in order that the function is continuous, the wave function's value at x is equal to 0 must be 0. So, therefore, this function that I have found, it has to satisfy the condition that at x is equal to 0, this function should satisfy the condition that it should be equal to 0. And not only that, when x is equal to L, what should be its value? It again should be 0. So, therefore, you have two conditions. In the region 2, you have to solve this differential equation subject to two conditions. The conditions, notice, they are at the boundaries of this region, and therefore, these are referred to as boundary conditions that the wave function should satisfy, because they are at the boundaries of the box. So, at the boundaries, what should happen? The wave function should be equal to 0. Why? Because outside the boundary, right, outside the box, the wave function is 0 everywhere. So, in order that the wave function is continuous, even at the boundary, the wave function has to be equal to 0, correct. So, we now will impose these two conditions on the wave function and see what the result is. So, your general function is this one, psi of x is equal to a sin kx plus b cos kx. So, what I am going to do is I am going to take that general form and put x is equal to 0, right, and satisfy this condition psi at x is equal to 0 is equal to 0. So, if you do that, psi at 0 will be equal to a sin 0 plus b cos 0, and that must be equal to 0. That is the result, and sin 0 I know it is actually 0. So, therefore, this term simply goes away, and cos 0 I know is equal to 1. So, therefore, what this means is that in order to satisfy the first boundary condition, b must be equal to 0. Then psi at x equal to L, right. This is the general form of my function. Okay, this is the general form of my function, but now I have found that in order to satisfy my first boundary condition, b must be 0. So, let me put that b equal to 0, this goes, and so that is my function now. And in there, if I put x is equal to L, what will be the answer? The answer is going to be a sin k into L, and this must be equal to 0. So, if you say that a product like a sin k L is equal to 0, then what are the possibilities? Well, one possibility is to say, okay, capital A must be, if you say product like a sin k L is equal to 0, there are two possibilities, either this can be 0 or the a can be 0. These are the two possibilities. But suppose I say a is equal to 0, I choose this possibility that a is equal to 0. Then what will happen? You see, if a is equal to 0, you will have to put that value of a here. That means your psi will be 0 even within the box. Correct? See, but we started with the assumption that the particle is inside the box, and therefore, the wave function for the particle cannot be 0 within the box. Correct? We are saying that there is a particle in the box, and if you cannot have a solution where you find that the particle is not within the box. In fact, the wave function, if you say that a is equal to 0, the wave function will be 0 within the box, not only within the box, even outside the wave function is 0. So, the particle will not be found anywhere, that is actually nonsense. So, therefore, a is equal to 0 is not acceptable, we are not going to take that as the solution. So, therefore, the only possibility is that sin k L must be equal to 0. That means, the value of k, see, L is the length of the box, that we cannot change. We have a box of a given length, but this k is something that we can choose. So, we have to have sin k L equal to 0. Only if sin k L is equal to 0 would I get an acceptable solution of my time independent Schrodinger equation. So, if k L is equal to what would this be satisfied? Well, if k into L is equal to n pi, in order to satisfy this condition, you will have to say that k into L is equal to n pi. Only if this is the way it is, will you be able to get acceptable solutions. And this n is a number, you see, it is an integer, it is constrained to be an integer. At the moment it appears that I can have n equal to 0, n equal to 1, n equal to 2, 3, 4, etc. Okay. But suppose I choose the case with n equal to 0. If you put n equal to 0, what will happen? You will have n equal to 0 here, you will have k into L equal to 0, that means k must be equal to 0, and if you have k equal to 0, what will happen to the solution? You will get 0 again, which is something that you do not want, I mean that is not an acceptable solution. So, therefore, among these values n equal to 0 itself we are going to omit, because it does not give me an acceptable solution, it does not give me an acceptable answer to my problem. So, therefore, the only possible values of n are 1, 2, 3, 4, 5, 6, etc. N has to be an integer, in fact, taking the value 1, 2, 3, 4, etc. and that actually means what? Well, remember this k is related to the energy. Okay. So, if you like, you can write E in terms of k. This is the expression, this is the relationship between k and energy. But now you find that k is constrained, k has to be equal to how much from this equation? K has to be equal to n pi divided by L. That means, you see, if you have E equal to h cross square divided by 2 m times n pi by L the whole square, only if this is satisfied will you be able to get acceptable solutions. For no other values of E will you be able to get acceptable solutions of the time independent Schrodinger equation, right. And what are these values? Actually, they are I mean, I could write it in this fashion: n square pi square h cross square divided by 2 m L square. These are the values of energy for which you can get acceptable solutions. And this n is referred to as a quantum number. N is referred to as a quantum number, and notice that it has come about automatically. All that I did was I tried to solve the Schrodinger equation satisfying the acceptability conditions, and once I imposed these conditions, I found that suddenly in the solution there is this quantum number n. Right. So, it comes out of the process of solving the Schrodinger equation. This you will find is the general situation. When we discuss the hydrogen atom again, you are going to find similar things. The three quantum numbers n, L and m that you would already know of, they actually arise automatically out of the solution of the Schrodinger equation when you impose the condition that the solution that you get has to be acceptable. Right. This will happen again and again. And further, what is the, this is the value of E, and what is the function itself, psi of x? It is of the form a sin k into x, but we have found that k must be equal to n pi by L. So, therefore, it is of the form k sin n pi by L. Okay. That is how the wave function is. And remember that this is for the region within the box. Outside the box, what will happen to psi? It will be equal to 0, right. So, strictly speaking, what I should do is I should say that it is equal to so much if x is less than, sorry, x is greater than 0 and less than L, and it is equal to 0 otherwise. Remember, you see, the equation that we were solving was just this equation, H psi is equal to E psi. This is the equation that we were analyzing. In fact, we were asking what are the eigenvalues of the Hamiltonian operator, and what did we find? We find that there are several different eigenvalues. Each value of n is going to give me a possible eigenvalue. So, if you put n equal to 1, you will get one eigenvalue, n equal to 2, 3, 4, etc. They are going to give you different eigenvalues, and each eigenvalue has its own associated eigenfunction. And further, if you remember postulate 3, suppose you make a measurement of the energy of the particle, what will you find? You will find that the answer will be of the form n square pi square h cross square by 2 m L square, with n having the value 1 or 2 or 3 or 4 or whatever, right. So, let us look at these states one by one, or maybe before doing that I should determine this constant capital A. I told you whenever we have a constant in front of the wave function, how do we determine that? The answer is that we will use what is referred to as the normalization condition, which implies that psi star psi right psi star psi dx integrated from minus, well, maybe I should be a little bit careful here. Strictly speaking, what I have to think of is capital psi. This object when integrated from minus infinity to plus infinity, the answer should be 1, that is the normalization condition. But as far as these states are concerned, as far as the states that we are thinking of are concerned, they are all stationary states, correct? They are all stationary states. So, therefore, psi star psi will not depend upon time. So, what is going to happen is that you would have psi star of x, psi of x. This product is nothing but psi star of x into psi of x into dx. And further these psi's, you see, they are 0 outside the box. So, it is not necessary for me to integrate from minus infinity to plus infinity, but it is sufficient if I integrate from 0 to L, which is the region of the box. So, this integral is actually, this is equal to integral 0 to L psi star psi dx, and this must be equal to 1. But now my function is actually psi of x is equal to a sin n pi x by L. So, I am going to use that in this equation. I will get a sin n pi x by L multiplied by psi star and dx, and I will have to integrate from 0 to capital L. This must be equal to 1. But when you look at the function, you do not find any square root of minus 1 anywhere. There is no I inside this. So, therefore, this star has no effect. Complex conjugation, only if there is minus square root of minus 1 sitting inside somewhere will it have an effect. So, psi star is actually psi itself. So, effectively this will become a square integral 0 to L sin square n pi x divided by L into dx is equal to 1. So, this is the condition that will determine the value of capital A. Now, how will you do this integral? I will very quickly tell you, because this is fairly straightforward. There is a trigonometric identity which says that sin square theta is equal to 1 minus cos 2 theta divided by 2. So, you can use that trigonometric identity in here. So, what will happen is that you will get a square integral 0 to L into 1 minus cos 2 n pi x by L divided by 2 into dx is the result that you will get. and then maybe I will not evaluate this. What is going to happen is that this term, when you do the integral, it will give you the answer 0, this term, and only the first term, which is half, will survive. And so, this is going to give you a square into integral 0 to L dx divided by 2 is equal to 1, and that is an integral that can be easily performed. You will find that a square into L is equal to 1, imply a square into L is equal to 2, implying that A must be equal to square root of 2 by L. So, therefore, we have determined the value of capital A, the normalization factor, and we can use that and write the solution. So, this A that is occurring in our expression, I can replace it with square root of 2 by L. So, let us look at these different solutions. Well, before I am going to look at the solutions, I notice that you see psi is dependent upon this quantum number n. So, psi is a function of x, in addition it depends upon this number n, which takes only integral values 1, 2, 3, etc. So, it is usual to put a subscript here to indicate that it depends upon n also, the quantum number, and similarly E will depend upon that number, and therefore, this is going to have a E subscript n. And as we have seen, n can have any value starting from 1 to infinity. So, therefore, how many eigen functions of the Hamiltonian operator have we found? The answer is that for each value of n gives you one eigen function and the associated eigenvalue. So, we have found infinite number of eigenvalues and associated eigenfunctions. So, we look at the first eigenfunction. The first eigenfunction would have n equal to 1. Okay. If n is equal to 1, I will have the function which is I1 of x, it will be given by square root of 2 by L sin pi x by L. The associated eigenvalue will be E1, which is equal to, what is the expression? In that expression which is occurring there, you will have pi square h cross square divided by 2 m L square. If you think about it, you will realize that this is the stationary state that has the lowest value for E, right, because n is equal to 1. Any other solution will have a larger value of E, and therefore, this is the lowest possible stationary state of the system, and its energy is equal to pi square h cross square by 2 m L square, and the wave function actually is square root of 2 by L sin pi x by L. And if I were to make a plot of this function, how would it look like? Psi 1 of x is going to be plotted along the vertical axis and x along the horizontal axis. So, running from 0 to capital L. In this region, it is not even necessary for me to plot the function, because in this region as well as in that region, I know that the function is 0. So, what is of interest is the value of the function within this box, and sine functions, we know how they depend. They are actually sinusoidal, so to say, they represent waves. So, therefore, if you made this particular function, if you made a plot of it at this region where x, at this point where x is equal to 0, the function will have the value 0. At x is equal to L, again the function will have the value 0. And if you think of the middle of the box is L by 2. If you put L by 2 in here, what will happen? You will get sin pi by 2, and remember sin pi by 2 is equal to 1, right. So, therefore, if you make a plot of this function, the answer that you are going to get is this. So, this is the way actually if you represent a sinusoidal curve, it would go like that, correct. This is how a sinusoidal function would look like, but all that is happening is that you do not have the other parts, you have just this part. So, this is the wave function for the system. Psi 1 of x would have this behavior. And of course, when you encounter such a wave function, you will get what is the information that you can get this wave function. This is the state that has the lowest energy, and for this function it would be very interesting to make a plot of psi 1 of x square. Why? Because if you are calculating psi star psi is the probability density, but there is no I in this function. So, therefore, psi 1 star psi 1 will be equal to psi 1 square. So, this is your probability density, and if you made a plot of that against x, how would it look like? Okay. It would look roughly the same, but there are slight changes. What actually happens is, I mean, the way it behaves near x is equal to 0 is changed. The function actually, if you make a plot of it, it would look like this. So, that is how the function would look like. Okay. What is the difference actually? The difference between this plot and that plot is, see here, if you look at the slope of this curve at x is equal to 0, the slope is finite, it is non-zero, while the way I have drawn here, this slope has the value 0. That is the difference between the two plots. Otherwise, it is almost the same. I mean, they look the same. And then, if you have such a probability density, and if I ask you what is the most probable position of the particle, answer is extremely simple. The most probable position for the particle is actually the center of the box. So, the particle is most likely to be found at the middle of the box, which is L by 2. Now, suppose you think of the next possible function, which is psi 2 of x. What will happen? The function will be square root of 2 by L sin 2 pi x by L. The associated eigenvalue or the associated energy will be 2 E2, which will be equal to 4 pi square h cross square divided by 2 m L square. This will be the associated eigenvalue. The energy is greater than the previous one, right. And if you made a plot of this function against x, how would it look like? Well, it is actually quite simple. At the boundaries of the box, the function has to vanish, but in addition to the boundaries, if you look at this function, where is my function? Where did I write it? Here is the function. Suppose you look at the function at the middle of the box at x is equal to L by 2. What will happen? If you put L by 2 here, you are going to get sine of pi, which is actually 0. So, that means at the middle of the box also the function is 0. So, would you like to guess? Actually, you can make a plot, but we can even guess. What will happen is that the function will start with the value 0, it will increase, reach some maximum value and then decrease and reach the minimum, not the minimum, reach the value 0 at the middle, and then how will it continue? Well, the way it continues is it goes down, the function becomes negative, and then again at the other boundary the function becomes 0. So, what is happening is that in this range the wave function is actually positive, while in that range the wave function is negative. But as far as the square of the wave function, which is actually the probability density, is concerned, the square will always be positive. So, if you made a plot of the square, maybe I can make the plot just below this, psi2 of x square. How would it look like? Well, the answer is it will start from 0, then it will reach a maximum value, then become 0 at x is equal to L by 2, then again increase and again becomes 0 at x is equal to L. This is the plot of psi2 square, which is the probability density, and if you are asked the question what is the most probable position for the particle, you will say, well, in this case there are two most probable positions. So, one is this point and the other is that point. This will be L by 4, while that will be 3 L by 4, and right at the middle of the box the probability of finding the probability density for finding the particle is actually equal to 0. Now, if you remember, this very much resembles the standing wave patterns that we had in a string. Remember that, you see, the simplest one, if you remember, there was no node. Just in the same fashion, the simplest possible wave function, you see, it does not get to the value 0 inside the box. The next one, remember, in that case there was one node, and that is exactly what is happening here. There is one node, right. And then if you think of the next case, what will happen? You will have n equal to 3. I mean, it is not even necessary for me to look at the function, but I know what is going to happen. Psi 3 of x, if you make a plot of it, how will it look like? Answer is very simple. Even without writing the function, I can make a plot of it. It is going to have, I know that it is going to have two nodes. So, this is the length L. I know that it will have two nodes, right. So, how will it look like? It would look like this. So, in this range the function will have the value which is will have values which are positive. Here in this range it will have values which are negative and then positive. That is how it is, and there are two nodes. You can make a plot of psi square in this in precisely the same fashion. It is very easy. How will it look like? Maybe I will just draw that also. So, that is how it will look like. So, I can say that if I have the wave function psi n, right, psi subscript n, n is the quantum number, then how many nodes will it have? It will have n minus 1 nodes, right. So, suppose the value of n was 10, what will happen? You will have 9 nodes, and how it will look like? It is difficult to draw, but let me just try. This is L, and I have to draw a wave function which has 9 nodes. So, imagine I plot psi 10 square. What is going to happen is I will have an appearance. Well, I hope I have put 9 points. Well, I need one more and a final one. This is L. And then what will happen? My probability will look like this. and they are all of equal height. You see, unfortunately the way I have drawn, they do not appear to be of the same height, but they are all of equal height. Now, this is a very large value of n. Right. Suppose I say that I have a particle which is not obeying quantum mechanics, but it obeys classical mechanics and it is inside the box, right, and I do not know where it is. So, therefore, all positions within the box are equally likely, and therefore, what is going to happen if I am speaking in terms of probabilities, the probability of finding the particle anywhere is the same. So, if I plotted that classical probability as a function of position, what would I get? What I would get, I will represent in this picture. I would get a straight line, something like that, correct, because the probability is the same, it does not depend upon position. So, this is what you get, and if you look at the quantum result, right, on an average it actually resembles, the probability is becoming almost the same everywhere, right, that is what is happening in the quantum result. So, as the value of n increases, the quantum mechanical result resembles more and more closely to the classical result. This is always the general situation whenever the value of the quantum number n is very large. The results that you obtain will be very close to what you would normally expect according to classical thinking. Okay. I think I can stop at this point. Thank you for listening.